My name is Eric. My day job is with the AWS security team, but I helped Marco and Kyle and the team with some of the security features for our new AWS IoT service, so that's what we're going to be talking about today. This is a story that we're all familiar with. We've got things, and they're getting connected. This ranges from ordinary consumer gadgets like thermostats and watches to industrial things like wind turbines, and I don't know, my car is on the internet now, which it's kind of nice that I know where it is and kind of disturbing that anyone with my password knows where it is. There's a lot of predictions here. Everyone has a set of numbers, but the way we think about this is that everything that could possibly become connected will become connected. So apparently, like even toothbrushes, I hadn't even thought about an internet-connected toothbrush, but apparently such a thing exists. So there's going to be lots of these things, and there's going to be lots of these things no matter what your definition of large is. I work for Amazon. We're a company that's used to scale. We talk about billions of things all the time, and even in that world, there's going to be lots of IoT devices. And the problem is that connected doesn't mean smart. The column on the left there is the internet stack that we used to have 30 years ago. These are the protocols that I grew up with on the internet. I kind of miss Archie, actually. It was kind of fun. But these are all clear text protocols. This is the academic network that turned into the internet. You look at the protocol stack on the right there, and right there again. These protocols are designed to accomplish specific goals, but security isn't one of them. And then when you peel the onion another layer, it gets even more complicated. The world of computing that we're traditionally used to, it used to be servers, desk side or in the back room, and then laptops came along, and now computing is about phones and tablets. But these devices are all basically the same. There's some tablet manufacturers out there that are very angry at me right now, I'm sure. But the set of hardware capabilities that these devices have, the form factors, aren't that varied. And you get into the world of embedded devices, and the form factors, the capabilities, the things that are built into the hardware are radically different. I don't have a device that I can't charge. There are a lot of embedded devices that have a battery in them, and that's a lifetime battery. When that battery is dead, you throw the thing out. So they're misers about power. There are devices where the CPU has just so many clock cycles, and every instruction counts. I have no idea. I think my phone has like 8 cores in it or something. Like, no one's counting instructions there. Some of these devices have hardware key storage. Some of them don't. So the world of IoT, the world of devices, is much broader and much more varied than traditional computing devices. So we have a simple goal. We have a device. We have the AWS IoT service. We want the device to talk to the service. We want the service to talk to the device. And we want to do so securely in both directions. Because this is a security talk, we are going to secure the heck out of this thing. And why, you ask? Because there's a bearded guy on stage frothing at the mouth screaming about security. This is a terrible reason to do security. You should do security because of the sensitivity of your data and your applications. And I hear this all the time. My day job is security for AWS. I talk to people inside the company, outside the company, and I hear my data isn't sensitive. In the IoT world, temperatures, fuel levels, vibration amounts, actuator positions, like very mundane stuff. Like, who cares that it's 83 degrees in the first floor of my house? But IoT isn't free. You're here at this conference learning about this. You're going to spend time and money implementing some IoT project. You have some business goal in mind. There's something you want to accomplish when you're doing this. So you've got your things. They're going to feed data into some data store. You're going to have some business application that feeds off of that data and does something to it, aggregates, filters, extrapolates, projects. Maybe you're going to have some humans involved in the loop. They're going to make decisions. The end result is that changes are going to happen in the real world. This is Internet of Things, not Internet of Abstractions or Internet of Concepts. We're going to make change happen in the real world. And so, in addition to protecting your data, you're protecting the decisions that you're making based on that data. So that's what you're protecting here. I've got this one thing in the lower left corner, and it's all lonely. It's not talking to anyone because it's evil. It is an evil thing. And it's feeding bad data in. And that bad data is going to propagate to your applications, it's going to propagate to your humans, and it's going to cause bad changes to happen in the real world. And some of these may be trivial. You may turn the temperature up in my house. I will be angry. I will go and I will turn the dial down again. Maybe we'll get into a fight. Maybe I'll rip the thermostat off the wall and put a dumb thermostat in its place. But that's not what we're doing here. We're talking about assembly lines, manufacturing processes, jet turbines, and wind turbines. These things are expensive. People's lives could be placed at risk if they're operating improperly. Some of it is just economic risk. We mess with the data so you think that your fleet is wearing out faster than it is, so you put it in for maintenance too soon, or that it's consuming more fuel than it actually is. And you order fuel before you have to, you accelerate capital. Maybe you take an assembly line out of operation because you think it's unsafe. Or worse, you leave an assembly line in operation because you incorrectly think that it is safe. So the extent to which you protect your IoT deployment should be driven by the most expensive decision that you could make based on your data, not the most expensive decision that you do make based on your data. So a rogue actor that gains access to this system, in many ways, is worse than fraudulent data. If I'm able to feed fraudulent data into the system, I have to perturb it using its normal inputs. I have to find the signal that will cause that system to behave irrationally, to behave incorrectly. If I have direct access to the system, I can just change its behavior. So we need to protect against this as well. Another pattern that I run into in security all the time is that things change. Today, your IoT deployment is simple. You're collecting a bunch of data. Like, everything is already instrumented. Like, it's already on the network. Like, you might as well collect the data and put it somewhere. Like, maybe it'll be useful someday. You're not making any decisions driven off of that data. So the most expensive decision you could make off that data is zero. It's not worth spending anything to protect it. But 6 months from now, someone's going to come to you and say, look, this data is gold. Like, I figured out that we can move this much faster, or we can accelerate delivery by this much, or we can optimize cost by this much. And you're going to think about it, and you're going to go for it, because that's the right thing to do. Like, you're in business to move faster, to delight your customers, to deliver more of whatever it is that you do. And you're not going to remember that 6-month-old decision where you said, this data isn't being used to drive any decisions. All of this data will eventually be used to drive decisions. And so as we go through IoT deployments, that's the operating assumption that we go in with. So in order to do this, in order to solve the problem that I've just posed, we need to make sure that when we talk to things, we're the only parties in the conversation. There are no eavesdroppers. We need to make sure that the things that we're talking to are actually the things that we think we're talking to. And then we need to control access across the system. We need to make sure that the things that we have in the system are the things we want in the system, that only the right data flows to the right places, and that it's a proper member of the AWS ecosystem. So the system that we live in starts with the AWS IoT service. This is a standard AWS service. It's even got a nice isomorphic logo, so you know it's good. We have things. There were supposed to be billions of these, but PowerPoint crashed, so I ratcheted back to 4. And the things are going to talk to the service. That makes sense. So blue arrows are things talking to the AWS IoT service. And you're going to have some set of actors in the system, humans, system processes, whatever. They're going to be talking to the IoT service as well, provisioning, management. So green is other actors talking to the AWS IoT service. And then, as Werner mentioned, there's a rules engine inside the IoT service. And we can drive data. We can process the data. We can aggregate it, filter it, and then we can drive that data into other parts of AWS. And we need to make sure that that's done sanely as well. So if we peek inside the service, if we zoom in a little bit, that is the best PowerPoint animation I have ever made. Thank you. We've got device shadows. These are our control plane representation of the devices that you've got deployed in the field. And so this is where we maintain state about your devices. So if they're intermittently connected, we maintain the last known state of them, so you can query that all the time. You can drive state changes at the shadows, and we'll propagate those out to the devices when they reconnect. And this is where you can execute control plane operations on the devices. So secure communications with things. We have blue arrows. The blue arrows are MQTT. It's a standard queuing pub-sub protocol. And it's one that's supported broadly in embedded devices. It's designed to be a lightweight messaging protocol. There's a ton of software that's already written to MQTT. It's well suited to embedded development, embedded deployments, devices with constrained CPU and memory. So we support that for devices, for things talking to the AWS IoT service. And this is a sample MQTT packet snagged off the wire, and it looks like a bunch of hexadecimal gobbledygook. But it can be decoded. And this is not because I am a wizard, because I have mad networking skills. This is because I have access to Google, and I downloaded Wireshark. Literally, like, the download itself was the longest part of this. Literally 30 seconds worth of effort to decode this. This is clearly a publish message to a topic named foo/bar. It's letting me know that the temperature is 83 degrees. Anyone that wants these tools will have them. We should go in assuming that anyone that wants to fold, spindle, mangle, or mutilate MQTT packets can do so. And that's fine. MQTT was intentionally designed as a lightweight protocol that didn't address security. It's used in many applications where it's perfectly reasonable to use MQTT natively. But we're talking about devices talking to the AWS IoT service over the open internet. We need to address security. And because MQTT doesn't have a mechanism for that, we need something outside of MQTT. The answer is mutual authentication TLS. This is a human being. They have a web browser. They're going to talk to the Amazon.com retail site. They want to go shopping. They're going to connect to Amazon.com, and Amazon's going to present a certificate. This certificate is public data. Literally, any one of you sitting here now could go download that certificate. We present it to every single TLS connection to the Amazon website. It is truly public data. We've also got a private key that corresponds to the public key embedded in that certificate. And we go through a challenge-response dance with this caller, and we prove that we're in possession of the private key that corresponds to the certificate without exposing the private key. And by proving that we have that private key, we authenticate ourselves. Now that you get the green lock in your browser, everything is safe, you know you can type in your credit card number. Note that we have no idea who that human is. They have not authenticated to us. This is an anonymous connection from their end. That's why you still have to sign into your Amazon account once you've connected. We have a very similar diagram in the MQTT world. We have the device. We want to talk to the AWS IoT service. Brings up a session between them. We have exactly the same protocol. The service presents a certificate, cryptographically proves that it's in possession of the private key, and we've authenticated the service. We go through the same dance in the opposite direction. The client is in possession of a certificate, proves that it's in possession of its private key, and now the service has authenticated the client. This is mutual authentication. We've each authenticated the other endpoint. So now we've got confidentiality and integrity on the wire because of TLS, and we've got mutual authentication because we've both presented certificates and proven that we are who we claim to be. Green arrows are not blue. There's something else going on here. These are standard AWS API calls. This is SSL, HTTP, AWS Auth, exactly as it works in the rest of Amazon. So in contrast to mutual Auth TLS, we've got some human, an IAM user, something like that, that wants to talk to the service. They're going to authenticate the service using the certificate exactly like you do if you're talking to EC2 or S3 or any of our other services. But then to authenticate the caller has a set of AWS API keys. It's an access key ID and a secret. And we don't authenticate the channel with AWS. We authenticate each API call. So we sign each API request, and we send those in, and then the service validates those requests. This is exactly how every single API call to SNS, SQS, SimpleDB, et cetera, work. That authenticates the caller. So now we've got mutual authentication in both cases. It is exactly as different as it needs to be. The whole goal of this was to support MQTT. MQTT doesn't support AWS API keys, so we needed to be different there. Server authentication, confidentiality, all of the other bits of the protocol are as similar as we could make them. Now, I claimed that I have this certificate provisioned on my device. And really, it's all about the private key. The private key is the cryptographic identity for the device. Just as the AWS or the Amazon.com private key is precious to us, we protect it carefully, the private key for your device is its cryptographic identity. That's what makes it who it is. And so we've reduced the problem of provisioning the device to the problem of securely installing the private key and certificate on the device. There's two ways that we support for doing this. The first is simple. It's a single API call. You call into the service, you say, create keys and certificate, which shockingly creates keys and certificate. So we're going to generate a key pair, we're going to assign the public key into a certificate, and we return those to you. It's then your job to install that on the thing by whatever means makes sense for your device, whether that's over a USB cable or a JTAG port or however you provision things to the device. To actually accomplish this in the CLI, you just call AWS IoT, create keys and certificate. You get back a JSON formatted response. It's a single command. You can see that last entry there, the certificate ID. It's very long, so I snipped out the middle of it. There's more hexadecimal that goes in there. That's the identifier. That's the globally unique system-assigned identifier for that certificate. We also return it to you in ARN format. ARN, A-R-N, is an Amazon resource name. These are consistently used across the platform. So S3 buckets and objects and EC2 instances and SQS queues and Kinesis streams all have ARNs. It's our consistent way of naming things in the AWS ecosystem. And then you get back the certificate and the key pair, both the public key and the private key. The downside to this is that we generated the key pair, including the private key, and that had to be moved across the network. Now, we take this very seriously. That private key needs to be protected. That's the cryptographic identity for your thing. So we forget it. We never write these to disk. And that's important. There is no API to refetch the private key. If you forget the response to create keys and certificate, you can never get that private key back. So we're going to take good care not to write your key pairs to disk. The connection there is protected with TLS. So you've got confidentiality on the network, but then it's going to wind up on your laptop or whatever client you're using. The key is moving around. And in some cases, if you've got hardware key stores, you can't move keys around. If you've ever used a smart card, the SIM cards that go in your phone, things like that, they generate the key pair in the device, and the key can't be exported. There is no verb for export key. And so in those cases, you have to have the client generate the key pair. So in this workflow, the client generates a key pair. Whether this is done in software on the device, whether it's done in a hardware key store, maybe it's burned in at the factory, and so when you get the system on chip, it's already got a key pair in it. And using that key pair, you sign a CSR, a certificate signing request. This is internet standard stuff. We did not make this up. The CSR format is defined in PKCS number 10. This is how most of the certificates used on the internet are issued. Now, the CSR includes the public key, but it doesn't include the private key. So it just includes that cryptographic signature, proof that we have the private key. And so this means that the CSR is not a sensitive document. A malicious actor that obtained the CSR could at worst turn it into a certificate, which is a public document. So these things can be moved around the network with much less concern. So now that we have a CSR, we fetch the CSR from the device, and we call create certificate from CSR at the AWS IoT service and pass the CSR as a parameter. And shockingly, this will create a certificate from the CSR. We turn it into a certificate, send it back to you. You provision it on your device, and you're in exactly the same state that you were in before. There's a private key and a certificate provisioned on the device, except in this case, the private key never moved around the network. This is done using our own private internal CA. The CA is only used for AWS IoT. It is not a general purpose CA. Because of that, everything can be completely automated. It's amenable to automation even at very high scale. So to actually go through this is an example of me doing it on an EC2 instance. I used OpenSSL to generate a key pair, and then I used OpenSSL to generate a CSR as well. It turns out, and this is a true fact in general, that a CA is under no obligation to use any of the data that you provide in the CSR other than the public key. They can change any of the fields. And so because typically you're doing something like getting a certificate for www.amazon.com, that data is important and the CA is going to validate it. You're getting a certificate for a thing from a private CA that's only used for this one service. You can literally fill in anything you want. We will ignore these values. The only value that we rely on is the distinguished name in the certificate, which we set to be that globally unique ID. So then you call create certificate from CSR, you pass in the CSR that you just generated, and you set it as active, and you get back almost exactly the same response as you got back when you created the certificate and keys, except that we don't include the key pair because you already have them. I keep saying, the private key is the cryptographic identity. It has to be protected. So I generated this on my EC2 instance, I borked my UMask, and so now this key pair, which includes the private key, is sitting there on disk world readable. Not the best security protection. If this is a test and dev machine, chmod is bar-raising security. Just removing world read permissions is probably a reasonable place to stop. And that's a common thing in security. It's not about stopping all possible badness. It's about taking an appropriate investment to mitigate the risks that are likely. The level of protection you go to should depend on the threats that you're going to face. If this is a dev system that's never going to leave the lab, stop here. You've spent enough. Then there's a fork in the road. Things tend to face either software threats or hardware threats. And it depends on the thing and the application it's being used for, and how valuable the thing is, how valuable the data is. If your thing faces software threats and it's a general purpose Linux box, there's things like chroot and SE Linux. There's a whole body of literature on this. A lot of these embedded devices have fun things that came out of the DRM efforts that they use on other embedded devices like tablets. So there's things like one-time programmable fuses that you can use to protect the private key. Again, because of the vast variety of hardware that's used in these embedded devices, it's hard to give specific advice. We've got a whole bunch of dev kits that you can pick up that are designed to work with AWS IoT. They're going to come with guidance. You can stop by the booth. We've got people there that can talk to you about your exact use case and give you guidance. If you've got hardware threats, that's when you get into the fun things, TPMs and smart cards. If you can't even trust the physical environment in which the thing is deployed, you get into FIPS-style controls like tamper switches, where if someone opens the box inappropriately, it zeroizes itself. Again, there's a broad array of things that can be done here, and so picking the right one is probably best done in context. Identity revocation. We can revoke identities. You've issued a certificate, you can list it here, you see that same description there. You do not get back the private key, we don't have it. You only get back the certificate. It's active, that means it can be used. So we can call update certificate and set the status to revoked. And shockingly, it's now revoked. This immediately invalidates this certificate. There's no dealing with CSRs and OCSP and all of that complexity. Because this is a closed ecosystem, because the only actors in this system are your devices and our service, we can make this work very rapidly and very reliably. And so if you have a thing that you are suspicious of, you think something has gone wrong, you can very quickly knock it out of the system. Now, amusingly enough, the revoke action cannot be revoked. It is irrevocable. So this certificate is now forever dead. It will never, ever make another API call. But you can use that same key pair if the key pair is safe. Let's say it was just a test. You wanted to make sure that I wasn't lying to you about revoking certificates, so you did it, and now you want this thing to work again. Or it was a game day, or it turns out that the threat wasn't real. For whatever reason, you want to make this thing work again. Even if it has a hardware key pair burned in at the factory, you can just go through the CSR dance again, get another certificate signed, and it's back in business. But it's very important. It is absolutely critical that every one of your things have a unique certificate. That certificate is its identity. If you have an army of things and they all have the same certificate, we will not be able to differentiate between them at the control plane. It is also critical that all of your things have distinct key pairs. If just the certificate is compromised, you can reuse the same key pair, you can re-sign again, you're good to go. If that key pair is compromised, your entire product line is compromised. Every single device that has that key in it is now suspect. So you should always use distinct certificates and distinct keys for every single device. So we know how to talk to the devices. We know who the devices are. Now we need to bootstrap them in the system. So that's this arrow here. We'll assume it's an IAM user managing the service itself. This is configuring the devices and making them active members of your instance of the AWS IoT service. And because this is a standard AWS service, all of the IAM richness that you get with other AWS services work here. So IAM users, identity federation, EC2 roles for instances, it all just works. If you've used this elsewhere in AWS, this will be easy. So if I want to control what this user can do, button needs to work, I assign a policy to them. So I've decided that this user should be able to manage certificates. And I've listed there all of the API calls that allow this person to manage certificates. So the only thing that you can do with these keys is call in and manage certificates. Everything else is going to be denied. And one important part about this policy application, and it applies to all of the policies that we're going to describe in the system, is that you can always change your mind. You can always add a new policy. It'll propagate very quickly across the system and be enforced. And so none of these decisions are final. And in order to make this API call, this principal has to have a set of API keys. Issued however you issue your AWS API keys. So this is another example of a policy. This is not a very realistic policy. I don't expect anyone to actually use it in production, but it's an example of the kind of flexibility that the AWS policy language gives you. This principal is allowed to call one API call, update certificates. We did this because we intend for them to be able to revoke one certificate, but it's scoped. You can see there's a specific resource called out there. So they can only make the update certificate call and only on that one resource. If they attempt to do anything to any other certificate, that call will fail. And we've added a source IP address condition. They can only do it if they're coming from that source IP address. So for example, this could be your server that's watching to make sure that the thing is behaving itself. And it can revoke that one certificate. It has no other privileges in the system. And if the keys are stolen off your server, they can't be used anywhere else. So again, this policy is not terribly useful in the real world, but it's the kind of thing that you can express using our policy language. In many cases, you have humans involved. Humans are bad at remembering keys. I'm bad at remembering passwords. They all wind up being the same. I write them down on sticky notes. Maybe you're all much better at this than I am, but typically humans aren't good at this. And so we like to use identity federation. As an AWS administrator, I have a smart card. It authenticates me against our corporate directory. So I can plug my smart card into my laptop, and I can authenticate against our corporate directory. The corporate directory says, this is actually Eric. And the corporate directory returns to me a set of temporary AWS API keys. And then I can call into the AWS IoT service. This is not unique to the IoT service. This works across the entire AWS platform. We have customers that are doing this all the time. If you're already using identity federation with AWS, it'll just work with the AWS IoT service, assuming you permit it in your policies. Now, we need to actually move data around. The whole purpose of this was to collect data from the real world to affect change in the real world. We need to start moving that data. And one of the ways you can do that is over the AWS APIs themselves. And so this sample policy allows me to call in and get the thing shadow for a thing named mything. Again, we're creative at naming. It also allows me to call publish on this special topic. And this is a magic topic. The $AWS/things is mapped by the service to the thing's shadow. So by giving this policy to a principal, I've allowed them to get input to the thing's shadow. So now I can interact with my thing. And one of the interesting capabilities that we've got is we have a mobile identity service called Cognito. Cognito offers mobile identity management and data synchronization for those mobile users. So a mobile application can authenticate against Cognito. Cognito can give them a set of temporary AWS API keys, and then they can call into the service. And the reason that this is a safe thing to do is that we have these special policy variables. The highlighted yellow stuff, the Cognito identity, that gets substituted by the Cognito service for the authenticated user ID. So I set this one policy once, and when I log in, I get access to my thing. And when Alex logs in, Alex gets access to his thing. And this applies to all of your users. So it's one policy. You don't have to own a directory. Cognito manages everything here. And so, one, you can use mobile devices as things. My phone is packed full of sensors. I can turn it into one of the devices in the AWS IoT ecosystem. And two, you can build IoT-enabled applications, and all of the boxes on this chart are owned by AWS. None of them are owned by the application developer. They own the policy, they own the rules, but they don't have to run any infrastructure. For MQTT, we have a similar story. Remember, inside the service, we've got the device shadows. And the device shadows have ARNs. They're first-order members of the AWS ecosystem, so we can hang policy off of them. So here's a sample policy attached to a device shadow. It allows it to publish to a couple of topics. It's not a very exciting policy, but now we've got a thing that's connected to the service and it's authorized to feed data in, which is what we were trying to accomplish. A richer example is this policy here. This is basically the same policy that we just applied to that IAM user, but it's MQTT, it's pub sub, it's not get thing shadow. But it's exactly the same set of privileges. I can get input to the shadow for the thing named my thing. To actually accomplish this in the CLI, we put the policy in a flat file. Use your favorite editor. Hardcore people use cat and Control-D. Then we create a policy. This is a call into the IoT service. It basically just uploads the policy document and associates a name with it. And again, being the creative people that we are, we named it my thing policy. And we get back a response, and it actually includes the entire policy document in the response, which is quite long, so I elided it. But it's got the name and the ARN for my thing policy. And then we attach that policy to the certificate associated with that thing. And so we have just done exactly the same thing that we did earlier. We have a policy, we attach it to an IAM user, we have a policy, we attach it to a thing shadow. And so we can constrain what actors in the system can do, all using the same AWS policy language, all using the same access control primitives. And so to the extent that we can, we've converged these two protocols. MQTT and HTTP are different. The way clients authenticate is different. But they have to be different because the whole point of doing this was to support MQTT. Everything else about this is the same. And so it allows you to swap between protocols. It allows you to change your mind about how your things are going to communicate with the ecosystem. And the changes don't ripple throughout the entire installation. So we have this rules engine. We have the ability for AWS IoT to talk to other AWS services on your behalf. These green arrows that we've not yet discussed. So with these rules in aggregation, you can do all sorts of clever things. You can say any temperatures that are in excess of 90 degrees get averaged and get pushed into this Kinesis stream, or something like that. You can automatically publish new data to DynamoDB, process it using Lambda. Like, you can stack this together however you want. And because this is part of the AWS ecosystem, we can use the same mechanisms that we use elsewhere in AWS to restrict this access. You want the AWS IoT service to be able to act on your behalf within the bounds of the rights that you want to give it. You want it to be publishing data to your thing table. You don't want it to be publishing data to your inventory tracking table. And so in order to do this, we need to create a role, an IAM role. This is a standard AWS concept, and it's used broadly across the platform. The first thing we need is a role trust policy. There's going to be two policies involved here. The first one is all about who can assume the role. So this policy here says that the IoT service can assume the role. We create the role at the AWS IAM service. We pass in the name we want, which again, creatively is thing actions role, and we pass in that role policy document. And so this creates a role. The role has no privileges at this point. It can't do anything, but the IoT service can assume that role and act on your behalf. The next thing we need is a policy for the role, an action policy. And in this case, I've given whoever can assume this role the access to put or update items in one DynamoDB table. So it's very constrained access. It's surgical access to my DynamoDB table. I create that policy, and then I attach that policy to the role. So you've got the role trust policy. Who can assume the role? You create the role. You create the policy that you want the role to be able to perform, and you associate that with the role. And so the net result here is that the AWS IoT service can put and update in exactly one DynamoDB table, which is exactly the level of access you wanted. And if you've used these mechanisms elsewhere in the AWS platform, it's exactly the same. So now that we've got all of this, how do we actually use it? How do we make devices, functional devices, that we can sell to end users? And I've got two scenarios here to go through. The first is an industrial device, which, for the sake of the example, has a hardware key store on it that's burned in at the factory. And it's sold to the end user explicitly as an AWS-enabled device. So they're buying it specifically because it works with AWS IoT. And in order for that to be true, it needs to have a key pair, it needs to have a certificate, it needs to be bound to some application. And so the first person to touch this device is the manufacturer. They're going to make a system on chip. And this device has a hardware key store. So part of the manufacturing process is that a key gets burned into that device. That key cannot be extracted, cannot be rotated. It's an inherent part of that system on chip. This SoC is sold to a vendor. And the vendor integrates it into whatever actuator, control, meter, monitor that they're building. And then they sell that to the end user. So at this point, the end user has a device. It's got a key in it, key that was placed there by the manufacturer. You can see the yellow border tracking it through its life. But it's not useful yet. So because this device has a hardware key store, the private key can't be extracted, the new owner of this device is going to call create certificate from CSR after generating a CSR. They're going to install the certificate on the thing. And so now we've got a certificate. The key was placed there by the manufacturer, but the certificate is owned by the end user. And then they can configure it with their application, and it can become a healthy, productive member of their factory or assembly line or wind turbine or whatever its purpose in life is. The other example, and I'm using a thermostat here because I happen to have thermostat clip art, but this could be a light bulb, a vacuum cleaner, apparently a toothbrush, like I still can't get over that one, a scale, whatever consumer device that you have. And it's going to be controlled by a mobile application, and it's sold to the end user as an internet-enabled device, not an AWS-enabled device. The end user doesn't necessarily have an AWS account. AWS is just plumbing here. It's helping the manufacturer of the device do useful things, but it's not explicit to the end user. So again, in order to make this real, we need a key pair, a certificate, and an application. This device does not have a hardware key store. The manufacturer doesn't do anything cryptographic here. They make a system on chip, and they pass it along to the vendor. The vendor, just to make the example interesting, uses create keys and certificate, the other method we have for provisioning certificates onto devices. They install the private key and the certificate as part of the thermostat manufacturing process. And so now we've got a vendor-owned key and certificate located on this device. And now we can sell it to someone. She takes it home. She gets out her phone. And now she's got to make this her thermostat. So the first thing to do is to get the device on the network. This can be done in many different ways. You type in the Wi-Fi password on the device, or you use an app on your phone over Bluetooth or ultrasonics. This is a well-studied problem, and it depends on the use of the device. But you get it on the network somehow, and it's already got a certificate on it, it's already got a key pair on it, so it's going to immediately start talking to that vendor's AWS account. It's already a part of the AWS IoT ecosystem. Now, the mobile app is going to try and log in to the AWS thermostat service. We have no idea who they are, so we're going to punt them. We're going to say, you need to go to Cognito and log in. So the mobile app goes to Cognito. They authenticate. If they need to be walked through the new account creation process, that's where this would happen. Cognito does data storage for users, so any customizations that this user has or creates will be stored in Cognito. So when the app comes, it authenticates to Cognito. It gets back an identity and proof of that identity. It also gets back whatever customizations exist. And they go back. They get redirected back to the thermostat service. The thermostat service knows now that they are authenticated. They've got a Cognito identity. And so it's going to call into the AWS IoT service, and it's going to set a policy. I drew the arrow here because I needed the room on the slide against the thing itself. It's actually going to apply it to the device shadow for the thermostat. And it's going to say that this thing, this device, is allowed to publish to the shadow for this one topic name. And I've got this %cognitoid syntax in there. That's not actually valid in AWS policy language. What I mean there is you just got back an identity, a cognito ID. It's a 10-character string from the cognito service. You replace that in this policy. So you're basically saying this is her thermostat. Then in the future, when this user shows up, they authenticate against Cognito, they get a set of temporary AWS API keys, and they can talk directly to the AWS IoT service. None of your infrastructure has to be involved at this point. And again, the reason that's safe is because when the user connects, we can use policy variables, and we can substitute in their Cognito identity. And so you've told the thing, you're allowed to talk about this one thermostat, and you told the Cognito user, you're allowed to talk about this one thermostat. So you're good to go now. This user can log in. Cognito hands them any customizations, any preferences they've got. They talk directly to the AWS IoT service. They can find out what the temperature is. They can set a new temperature, change schedules, like whatever it is that this thing is supposed to do. And so after we've gone through this claiming dance, we wind up with a device that's fully provisioned. It's got a Keypair and a certificate that are owned by the vendor, the manufacturer of the finished device, and it's bound to the application owned by the end user. And these are two paths through a very broad space full of a lot of options. They're just two examples of ways that you can use this service to support different business models. You support different methods. So depending on the capabilities of the system on chip, of the device itself, depending on the business model you have, whether you're explicitly selling something as AWS enabled or it's an end user device and you don't want to expose the use of AWS to that person. Like, I don't care that my thermostat uses AWS or whatever. I care that the app is awesome and that I know what temperature it is. We can support both of those. So the agenda that we opened with had 6 lines here, really 5 points. I think we've hit them all. We need to make sure that we are only talking to the things that we should be talking to. We need to make sure that the things that we're talking to are actually the things we think they are. We have 2 methods for doing that, 2 protocols for securely deploying certificates onto devices. And then we have flexible, consistent access control. So using the AWS policy language, you can control what the users, whether they're servers or applications or humans, can do at the AWS API endpoint, both for managing the service and for managing accessing data within the service, including mobile clients, identity federated clients, things like that. We've described how you can restrict access over the secure MQTT protocol that we have and limit what your devices can do in the system. And it's exactly the same policy language, it's exactly the same flexibility. And we've also talked about how you can use IoT, AWS, to grant IoT very precise, very controlled access to your AWS resources so it can take action on your behalf. And it's the same policy language across the board. And so the cool thing about this is that it's a collection of building blocks. They can be stacked in many different ways. And so you could field the devices yourself, collect the data, feed it into a Kinesis stream, and sell access to that data. That's a business model that could be built using AWS. You can build things that are AWS enabled. They're ready to go out of the box, like our industrial example. You can build consumer devices, multi-tenant applications where they're your things, but you decide dynamically who gets access to which things. Some interesting capture the flag kinds of applications that you could build there. And in many cases, you can build all of this without owning any infrastructure, without having to have any persistent infrastructure online. It's all done by AWS services. So there's a whole bunch of other sessions on IoT. If you have any interest, you should absolutely check them out. Thank you for the time, and I will be beaten if I do not remind you to fill out your evaluations. We value your feedback a lot. We'd like to know how we did both here at the conference and with AWS in general. Thank you.